But somewhere along the line there will be the need to join these panels together.
A clinch joint is made simply by bending one sheet tightly around another.
And this is a section of a clinch joint in a car door.
It should keep the water out, but we all know that door bottoms were notorious for rusting.
Why was that? Water can enter the door section through various routes, such as past the window rubbers, draining down to the bottom and getting drawn into the clinched seams,
where corrosion occurs. This is the anodic centre within the crevice.
And here is where the cathodic reactions take place, just outside the crevice.
And here is the rust between the anode and the cathode,
much accelerated by the presence of chlorides in this confined environment, even though these concentrations may be small, as they are in rainwater, for example. This is crevice corrosion.
There are several places where corrosion of this kind occurs.
Underneath the paint film,
between spot-welded joints,
and anywhere where surface coatings haven't protected the steel.
In fact, a whole battery of anti-corrosion techniques are employed to prevent corrosion.
In a clinch joint, for example, the inner panel is coated on both sides with zinc,
whereas the outer panel will only be zinc coated on its internal surface.
The outer surface doesn't need it.
Typically, the joint is sealed with an adhesive and a sealant and should be airtight. In addition, wax is sprayed into the gap and drainage holes introduced into the inner panel to let any water out.
All this protection is needed on door bottoms to prevent them corroding. Here is a clinch joint being made on a bonnet panel.
First, the adhesive. Since 1985, when zinc-coated panels started to be introduced, the proportion of zinc-coated steel in cars has steadily increased.
Now it's between 70 and 80% on Rover cars. To clinch the outer panel over the inner one, the workpiece is put into a press.
Coating a steel sheet with zinc adds about 20% to its cost, so it is expensive and not to be used unless it's really needed.
That's why you still find uncoated mild steel in cars, in areas where paint alone is sufficient protection, such as on the roof panel, for example.
The sheet steel surface takes paint extremely well, and so on many cars, cosmetic panels like the door, bonnet and wings are electrocoated with zinc on one side only, the inner side.
In the Rover 600, about 25% of the steel used is of this type.
However, with demand for even better corrosion performance, double-sided zinc-coated steels are being used more and more,
particularly for most structural members and the base assembly where maximum protection is needed. Double-sided zinc-coated steel can also be produced by a different process than that of electroplating. And seeing how this is manufactured takes us to British Steel's Llanwern plant in South Wales.
Here, sheet steel is immersed into molten zinc at 455 to 465 degrees centigrade in a process known as hot dip galvanizing. Then, by careful heat treatment within a vertical furnace located above the zinc bath, the zinc coating is converted into a layer of iron-zinc alloy.
In the tempering process which follows, fissures develop in the surface, and these help the paint key into the coating. Also, within the alloy, a hard phase develops.
And this means that less zinc is melted out of the surface layer when it's spot welded. Molten zinc reacts with copper in the electrode, forming brass, which you can see in these spot welds quite easily.
It also affects the electrodes, which have to be redressed frequently to maintain the correct current density at the tip.
Ensuring welding efficiency has been a major achievement here on Rover's assembly line at Cowley.
But it's the cost factor that really makes the annealed hot-dip galvanised steel attractive.
Apart from uncoated steel, it is the cheapest material to use.
In the Rover 600, it has become the predominant steel type.
And there is an obvious incentive to find ways of incorporating it into the vehicle more and more, ultimately for outer surfaces too. Now for a subtle change of emphasis in anti-corrosion strategy. Can we do better than just using zinc?
Electroplating a zinc-nickel alloy provides a thinner, harder layer that's better for welding.
Increased protection against corrosion can be achieved by coating this layer.
First with a very thin deposit of chromate to help bond a lacquer onto the zinc-nickel surface.
In the oven, the lacquer is cured to give an organic polymer about 1 micron thick.
The whole sandwich of zinc-nickel alloy, chromate layer and polymer can be of the order of 5 microns thick,
giving the same protection as the alternatives whose coatings are a little thicker at between 6 and 8 microns.
Now this may not sound much of a difference, but the thinner the coating, the easier the material is to work with.
The main disadvantage is it's the most expensive of the coated steels.
Despite this, it is used quite extensively within the automotive industry.
So the cost equation is not always the limiting factor.
The organic polymer layer is very like a paint. So let's look at what's involved in this traditional yet ongoing method of protecting metals from attack. After 331 panels have been given 4,500 spot welds, the body in white, as the industry romantically calls its creation, is given a thorough clean, including a hot bath in an alkaline mix of complexing agents and surfactants, followed by a cold rinse before treatment with a colloidal solution of titanium phosphate.
The body in white emerges covered in minute crystals, which are going to act as nuclei for the climax of the process, full immersion in a tank containing zinc, manganese and nickel phosphate, and an oxidizing agent.
Here, the object is to coat the metal with a crystalline phosphate in a product hopefully looking like this, and in a layer up to 3.5 microns thick.
But because the material to be coated varies, it can be iron, zinc or a zinc alloy, the phosphate layer can end up having a range of composition and structure. So the chemistry of the process is carefully controlled. Its prime purpose is to promote adhesion between the metal surface and the subsequent paint layer.
Any gaps in the phosphate layer leading to the unreacted metal